So thank you very much for the kind introduction. My name is Benjamin JUNGFLEISCH. I'm an associate professor in the Department of Physics and Astronomy here at the University of Delaware. I'm going to talk about light and microwave-induced spin current and spin-to-charge current conversion in magnetic quantum material heterostructures. And more specifically, I'll talk about ferromagnet 3D topological insulator heterostructures. I want to thank the organizers for inviting me and giving me a chance to speak about those results. Unfortunately, I cannot be there in person because I caught COVID and I figured it's best for me to stay here. But I'm pretty sure that you are enjoying an exciting workshop in a wonderful location. Okay, so this work is a collaboration between the University of Delaware, Morgan State University, and NIST. And in particular, I want to highlight here the efforts of my graduate student, Weipeng Wu, who was in charge of the Terahertz spectroscopy measurements that I'm discussing today. The samples, topological insulator ferromagnet heterostructures, were grown by the Budani group at Morgan State University, and they also characterized the samples by gigahertz spectroscopy. Some of the early work that I'm going to show you were done in collaboration with Argonne National Laboratory. We are very grateful for financial support by the National Science Foundation through the MERSAC program, Yudi Chan. So we are here because we're interested in terahertz spintronics, so I'm going to keep it rather brief. Terahertz radiation falls between the infrared and the microwave frequency range in the electromagnetic spectrum, and there's not only a vast number of applications, but there's also lots of interesting physics, especially spin physics, to explore in this frequency regime or on these timescales. Now, a spintronic terahertz emitter is conceptually very easy, very simple. It consists of a ferromagnetic heterostructure, for example, iron as a prototypical ferromagnet and a heavy metal layer such as platinum. And then if we shine the femtosecond laser pulse onto these heterostructures, we excite the system, we promote electrons from below the Fermi level to above the Fermi energy. And because iron is a ferromagnet, we have an imbalance between majority and minority spins, so spin up and spin down electrons. And if they get promoted above the Fermi energy, they have different group velocities. As a result, we create a ultra-fast spin current that diffuses from the iron layer into the heavy metal layer, into the platinum layer, where it's converted into a charge current by means of the inverse spin Hall effect. And this results then in the emission of terahertz transients. Now, this process is rather efficient. We can get a comparably large signal strength. The biggest advantage probably of the spintronic terahertz emitters is that they are broadband, easy to fabricate, and inexpensive. Now, in my group, we did not only look into the inverse spin Hall effect as a rectification mechanism from spin to charge currents. We also looked into Rashbach interfaces featuring strong Rashbach spin orbit coupling. And we showed that we can use the so-called inverse Rashbach-Edelstein effect to convert this ultra-fast spin current into a charge current and observe terahertz emission, and can control this using these systems. Now, in this particular work, it's shown here schematically. We used a tri-layer system where the ferromagnet was a cobalt-iron boron layer, and the Rashbach interface was between two non-magnetic materials, silver and bismuth. And as you can see here in this figure on the bottom, we see a large enhancement when we bring silver and bismuth into contact on top of the cobalt-iron boron layer. So this is due to the inverse Rashbach-Edelstein effect. More recently, we have looked into how we can manipulate the terahertz emission using microfabrication. In this case, we used stripes made of microfabricated stripes made of iron and platinum, and then we illuminate the sample and measure the terahertz spectrum, and we saw that we can manipulate the spectrum based on these microstructures, based on the dimensions of these stripes. We also looked into how we can control the polarization state, the terahertz polarization, using the remnant magnetization. I want to spend a few moments explaining the concept and the results we obtained. So let's say we have such a disk, and we chop off the lower portion of this disk as it is shown here in this schematic. So we introduce a mirror symmetry breaking. And if you now imagine we apply a magnetic field along this symmetry breaking cut, in the remnant state, we would expect 100% chirality, in this case, a right-handed chirality of the magnetization. Now, if we were to use the same kind of system and now apply the magnetic field perpendicular to the cut, in the remnant state, we would expect a 50-50 chance to get left-handed or right-handed magnetization texture in our chopped disks. Now, so we have either the same chirality or a random chirality, and if we now have a multitude of these disks and we shine a laser on them, we would expect that we see in this first case a terahertz emission both in the x and in the y direction due to the magnetization in the y and the x direction respectively, and no terahertz emission or a negligibly small signal for the random chirality because overall we get a cancellation. So to test this hypothesis, we conducted micromagnetic simulations and optimized our dimensions. We fabricated our devices. Here we use a tri-layer system made of platinum, iron, and tungsten. You can see the dimension here that were optimized using micromagnetics. So now let's take a look. We apply here a field first along the symmetry breaking cut. And this is the result that we obtain for an angle of 0 degrees. We get both the x component and an EY component, again, because we have this chirality, this right-handed chirality, x and y component in the magnetization, and due to the inverse Spin-Hall effect, we would expect to see both components in the terahertz emission. Now we can rotate our sample in the remnant state without any field applied, and this is the terahertz amplitude as a function of the in-plane angle. We see a 360-degree periodicity and a shift between the EX and the EY component of 90 degrees. So this confirms that this is due to the inverse Spin-Hall effect. Let's apply a field perpendicular to the cut. We get a negligible system here. It's the same scale. It's much, much weaker. And we can now do the same kind of in-plane angular dependence. We see here the terahertz amplitude versus the angle. It's but a flat, there's no signal. So we can control the terahertz polarization, or we can switch on terahertz just by applying the field in a certain direction. So this tunability of the polarization state is facilitated by the underlying magnetization texture, which of course is dictated by the shape of our microstructure. These results also give insights into the underlying physical mechanisms of how a non-uniform magnetization state can affect the ultrafast spin current generation process. Now, in the remaining time of my presentation, I'm going to focus on spin current injection and spin-to-charge current conversion in ferromagnet 3D topological insulator heterostructures. And I'm going to compare gigahertz inverse Spin-Hall measurements in ferromagnetic resonance with the terahertz emission spectroscopy. These samples were grown by our collaborator at Morgan State, Ramesh Budani's group. They use DC magnetron sputtering, and we use two different systems. So let me first describe the first one. Here we use iron gallium boron. Why iron gallium boron? It's a magnetostrictive material, so you can imagine this material could potentially be used to apply a gate voltage, an electric field with which you can manipulate the magnetization, and with that you get an additional tuning mechanism for the terahertz emission characteristic. So this motivated why we were interested in iron gallium boron. It's amorphous, it's sputtered, and as a 3D topological insulator, we use bismuth antimony. The second material system is epitaxial iron cobalt with a composition of 75-25. This material is interesting for spintronic and meganonic applications because it has a low Gilbert damping parameter, so you can do lots of interesting meganonics and spintronics with this material. And we wanted to see how it performs at ultra-fast timescales. As a topological insulator, we use bismuth tellerite, which is polycrystalline. The work on iron gallium boron bismuth antimony was published in PR Materials, and the epitaxial iron cobalt bismuth tellerite was published in Applied Physics Letters. So let's start first with the iron gallium boron bismuth antimony. So we grow the samples by DC magneton sputtering. We keep the thickness of the iron gallium boron fixed at 6 nanometers, and then fabricate a series of bismuth antimony thicknesses between 0 and 20 nanometers. And in the following, I'm referring to the different thicknesses as, so this is the thickness in nanometers, 6 nanometers, iron gallium boron that's fixed, and bismuth antimony 2. And I'm going to label this as A6B2. So the number behind the 2 refers to the bismuth antimony thickness. So this is magnetometry data that we collected for the bare iron gallium boron system in black. And I show here also 2 representative thicknesses of bismuth antimony, 2 and 8 nanometers. They all have a similar saturation magnetization, independent of the bismuth antimony thickness. And we find a small corrosivity field of less than 2 millitesla. So this shows the soft magnetic character of iron gallium boron with an in-plane magnetization. These results confirm that the position of bismuth antimony on top of the iron gallium boron does not affect the magnetization. So let me first discuss the gigahertz spectroscopy measurements. We do FMR to extract the Gilbert damping parameter, which allows us to calculate the spin mixing conductance. Second, inverse spin Hall effect measurements, which allows us to determine the spin Hall angle as well as the spin diffusion length. On the left-hand side, I'm showing the differential absorption we obtain by ferromagnetic resonance. On the top, this is 8 nanometers of bismuth antimony. On the bottom, this is the bare iron gallium boron sample. You can see a high degree of magnetic homogeneity in the iron gallium boron film, according to the Lorentzian fit. We can fit this with both symmetric and antisymmetric Lorentzian line coefficients, and extract the resonance line width as well as the resonance precision. So here we see resonance frequency versus resonance field. This can be fitted to the Kittel equation, which allows us to extract the effective magnetization, but we can also get, of course, the resonance field. And we see here there's a small variation both in the effective magnetization as well as in the saturation magnetization. So this suggests a metallurgically clean interface between the iron gallium boron and the bismuth antimony. On this slide here, in this plot, I'm showing the line width versus frequency. The slope corresponds to the Gilbert damping parameter. We extract this for the different bismuth antimony thicknesses. So this is the Gilbert damping parameter alpha. The line width is enhanced for the iron gallium boron bismuth antimony samples, and the rapid increase of alpha shows that there's an efficient absorption of the spin current in the bismuth antimony. This data allows us to calculate the spin mixing conductance, and as we already see here from this plot of the Gilbert damping parameter, the spin mixing conductance looks rather unusual. So usually for metal, we would expect to see an increase in the saturation. That's not the case over here, and we think that this is due to topological surface states that affect the spin mixing conductance in the system. By the way, here this red dotted line is as a reference. This is for permalloy platinum, the spin mixing conductance of permalloy platinum. You can also calculate, or excuse me, you can also measure the inverse spin Hall effect voltage that is shown here for the different samples. I show here the results for different field polarities. The sign reverses upon change of the field direction. And we can now fit this data to symmetric and antisymmetric Lorentzian line shape. The symmetric contribution is due to spin pumping induced inverse spin Hall effect. in the bismuth antimony, and we cannot rule out that there is some self-induced inverse spin Hall effect in the iron-gallium boron. The antisymmetric component comes from the anisotropic magnetoresistance and potentially some contribution from anomalous Hall effect. So this allows us to deconvolute this signal, and I'm showing here symmetric and antisymmetric contribution. From this data and comparing the results of iron-gallium boron bismuth antimony to the bare iron-gallium boron, we see that bismuth antimony has a positive spin Hall angle, and there's an opposite spin Hall angle for the bare iron-gallium boron compared to the bilayer. These results also allow us to calculate the spin Hall angle. It's rather small, about 1%. It's much, much smaller to what has been reported in second harmonic Hall measurements. And we think that this is due to the fact that in the second harmonic measurements, they apply a current. So there's a current flowing through the bilayer stack, and this is known to give a larger spin Hall angle than in this kind of spin pumping induced inverse spin Hall measurements. You can also extract the spin diffusion length. So this is the current density versus the antimony, bismuth antimony thickness. We get a spin diffusion length of about 7.8 nanometers. Doing the same for the asymmetric component, we get this interesting damped oscillator-like behavior as a function of the bismuth antimony thickness. And we think that this is due to the opposite sign of AMR in the iron-gallium boron and the bismuth antimony. So there is some kind of back and forth between the two AMR contributions. So how does it translate to the gigahertz? How do the gigahertz dynamics translate to the terahertz range? So we perform the measurements on the same type of samples. We excite our system with femtosecond laser pulses. I'm showing here the result for 20 nanometers of bismuth antimony, and when we reverse the field direction, the signal polarity changes its sign. So this speaks for the magnetic origin of the signal. We also compare here the bare iron-gallium boron sample, shown in green, with the iron-gallium boron bismuth antimony, in this case 3 nanometers. And again, we see here opposite signs for the two systems, which confirms what we saw in the gigahertz spin pumping measurements. There's a different spin Hall angle for iron-gallium boron and iron-gallium boron bismuth antimony. We also collected the terahertz amplitude as a function of the bismuth antimony thickness. Also calculated here the current as a proxy just by dividing the terahertz amplitude by the DC resistance. Overall, we find a really good agreement between the gigahertz dynamics and the terahertz dynamics and the material parameters that we extract. Now, to understand this further, we talked to our theoretical collaborators at UD-CHARM, and they did some linear response theory using the Kubo-Bastin formula, using a time binding model, and the results are shown here. So this is the spin Hall conductivity as a function of the number of bismuth antimony bilayers. And you can see that the spin Hall conductivity increases as the bismuth antimony bilayer number is increased. These two terms are the hopping terms. They correspond to the case with and without surface Rashbach effect. So this is just showing all the data, the modeling, the spin pumping data at gigahertz frequencies, and the terahertz spectroscopy measurements. And we see a very good agreement here between the theory and the two experiments at different timescales. So let me just briefly sum up this first part. We saw we have a metallurgy clean interface between iron-gallium boron and bismuth antimony. We found an unconventional thickness dependence of the spin mixing conductance, which we believe is due to effects of topological surface states. The spin pumping induced DC measurements allows us to separate the contributions of AMR and inverse spin Hall effect. We extracted material parameters such as the spin Hall angle and the spin diffusion length. And ultimately, we found a very good agreement between the experiment and the modeling. Now, in the remaining time of my presentation, I'm going to discuss these recent results on epitaxial iron cobalt bismuth telluride bilayer systems. Again, we compare gigahertz experiments with terahertz experiments. Let me first show you the gigahertz spin pumping induced inverse spin Hall measurements. So this is what we get. So this is the symmetrized voltage as a function of the field. Again, we do this as a function of the thickness. And we see here that the signal decreases as we increase the bismuth antimony thickness, at least in the spin pumping measurements. We can again fit this with symmetric and antisymmetric contributions, and we think that here in this case, the rectification effects play an important role in these measurements, especially for the bare iron cobalt system. So AMR is strong, and therefore we get a strong homodyne rectification for the iron cobalt system. So we have here both effects, inverse spin Hall effect, as well as homodyne rectification based on AMR. On the right-hand side, I'm showing you the current versus the bismuth telluride thickness, which allows us to determine the spin diffusion length. It's of the order of 1.8 nanometers. And we use also terahertz spectroscopy to study these samples. I'm showing here the result for the bare iron cobalt system. And we are exciting here from both the front and the back side, so either from the substrate side or from the film side. And as you can see, both signals have the same polarity. Therefore, we think that in this case, we have a significant contribution of magnetic dipole radiation, whereas contributions from AMR, anomalous Hall effect, and Zelf-induced inverse spin Hall effect are secondary to this signal. Let's compare this to the bilayer system. So this is iron cobalt bismuth telluride. Again, for exciting from the back side as well as from the front side. And you can see here now the amplitude is reversed. However, if we illuminate from the back side, the signal amplitude, the magnitude is smaller. So in this case, we have two contributions. One is from the magnetic dipole radiation, and the second one is the inverse spin Hall effect in the bismuth telluride. So in one case, both add up to each other, and in the other case, they oppose each other. This is the raw data, the time domain traces for the different thicknesses, and we can also plot here the terahertz electric field as a function of the bismuth telluride thickness, and extract the relaxation length based on a hot electron velocity model. And the relaxation length here is 2 nanometer, which agrees reasonably well with what we found from the gigahertz spin pumping measurements. In that case, it was 1.8 nanometers. So with this, I want to conclude. I showed you that we observe spin pumping induced inverse spin Hall effect in iron cobalt bismuth telluride bilayer systems. We revealed a significant contribution of AMR in the bare iron cobalt layers. We extracted the spin diffusion length obtained from the two experiments both at gigahertz and terahertz frequencies, and they agree reasonably well despite the drastically different time scale. Overall, I want to note that if FMR-induced spin pumping and ultra-fast spin current injections are promising complementary tools to investigate the inverse spin Hall effect. With this, again, I want to thank the National Science Foundation for supporting our MRSEC, and I'm looking forward to your questions. Thank you very much.